Good evening, everybody. It is once again Ted the Speed Learner, and I'm glad you're all here tonight. I am here tonight. We're going to have a great big live stream. I have been promising this to a lot of people for a long time now. I even made a notation at the end of the parade video. If you remember that, I went to the Blue Mountain Fall Festival Parade, and I made a reference to this. I told you guys I was going to do a very big live stream today. Okay, I actually said this weekend, but yesterday I had a lot of cooking to do, and there was no way I was going to be able to do a live stream and do all that cooking at the same time. So today I took naps. I got some stuff cleaned in my house. I am currently on vacation. That's why we're doing this. I can see I already got somebody in my chat here. Please let me know who you are. That way I know who I'm talking to, okay? There will be another live stream in September, and it will probably be about as large as what we're going to do tonight. Go figure, huh? Okay. Not a lot to tell you except for the fact that I have been made aware of the Adobe Photo Elements, and you guys have to get these great big subscriptions, and you're having to pay hundreds of dollars for something you guys can do for yourself. It's wrong that you're not doing this. So here's what we're going to do. I'm going to start right off the bat. Like I said, if you guys are watching me, if you want to leave a message on the live stream, fine. If you watch me later on, leave me a comment in the comment section down below. Let me know that you actually watched this, okay? Of course, as you know. Oh, hello, Rob. Nice to see you. Glad you're here. So I'm not sure who this Rob is, but I'm glad to see him anyway. So whoever wants to come in, let me know, and we'll go through this. And like I said, when it comes to Adobe Photo Elements, we're just going to let them know we don't appreciate them charging us hundreds of dollars, especially if you can do it yourself for free. That's right. Let me clear this up for you, folks. A lot of the software they're using, okay, is actually included in your web browser. And you're paying hundreds of dollars for something, for the most part, you could do all by yourself? Shamey, shamey. Well, we're going to get into this. There are a lot of terms and stuff that I want to cover tonight. This is good education for you people. One of the biggest things I'm seeing right now is I have people come in. I work in retail. They come into the kiosks. They don't even know how to work them. And these people are not like 70, 80 years old. I get that. Some of these people are like 25, 30 years old. Come on. You've had technology for years. You should know how to do this kind of stuff. You know what an application is. And if you don't, I'm going to explain it tonight. Real easy. Okay. So I've done a ton of research. We're going to take this step by step. Some of these videos, I'm going to put big time illustrations all throughout the video. So what you're just hearing is the audio part of the video. Oh, I see I have a second person in my live stream. I welcome you. Please just leave me a comment in the chat box. Let me know who you are so I know who I'm talking to. But like I said, I'm going to have these illustrations all throughout the actual video itself. All you're doing is hearing the audio portion of the videos that I'm going to create. Now, sometimes I'll just put it on my dry erase board, but sometimes I'm going to put it on other things. So there you go. And I've heard people like, well, there's not enough lighting in your room or all da-da-da-da. Let me tell you something. When you guys start paying me, that's when I'll improve all this stuff. But one good thing is that after tonight, I'm going to show you the means of drawing the foundation of the Bezier curve. Okay. Now, it won't be the Bezier curve in itself. I know you saw a post about that in the Facebook. Okay. I had this big post on Facebook saying I was going to do the Bezier curve. I'm going to lay the groundwork for the Bezier curve. And then after that, I will make the formal presentation on that. And that will be probably either in September or maybe next year. Who knows? But at least you'll have an idea of how the Bezier curve actually works when I get done with you. All right? So, let's get to work, shall we? I am well aware of people going back to school. I see I have a second person in my live stream. Welcome, welcome, welcome. Please let me know who you are. And the key is that when you go back to school, and I know, let me tell you something. When I was a kid, I hated the time when I was going to have to go back to school. I really did. I did not enjoy going to school, okay? But I'm here to make it better for you because I didn't have what I'm giving you, and it's wrong. So we're going to give you what I never had. All right? So if you're feeling bad about going to school, don't feel bad because we're going to take care of that, okay? You're going to learn a whole lot faster when I get done with you. I also wanted to make you aware that I have been making some changes on a lot of the videos that I have on my YouTube channel. You have probably seen new thumbnails. You've seen new playlists. I'm sure you saw that. There you go. Okay. So without any further ado, let's change things, shall we? That was terrible. Let's try this one more time. Good evening, everyone. It is once again Ted the Speed Learner, and tonight I'm going to cover the topic of the metal oxide silicon field effect transistor. And if you don't know what that is, I want you to watch this video all the way through. But before I start this conversation up, okay, let's get into this, shall we? All right, I'm going to start with an illustration here. Now, this is kind of going back to my unipolar transistor video that I told you there was a link to another video that you could watch that would explain the unipolar transistor a little bit better than I could. They had an illustration in there, and I'm going to give you this one. It looks like a TV with rabbit ears, but really it's not. This here would be germanium, and right above the germanium is this positive charge carrier layer, okay? And this gold foil would come in contact with this. And then they'd hook a battery to all this, okay? Actually, they're going to hook two batteries to all this, all right? And I'm going to have an illustration on this video that if you're watching me on the live stream, you're not seeing it right now, but you will see it when I actually make the video here. But anyway, let's get into this. What is a metal oxide silicon field effect transistor? Okay. Now, in previous videos, I discussed the topics of watt, amp, and volt. And I would suggest that before you watch this one all the way through, if you are not familiar with the terms watt, amp, and volt, I would head over to those videos and watch them. Okay. Now, in that particular set of videos, okay, I stated that electrical current flows in one direction while electrons flow in the opposite direction. Remember that? So let's say that you have a battery and there are electrons flowing from the cathode of the battery to the anode. Okay. If that is occurring, then electrical current is flowing from the anode of the battery to the cathode. But what does this have to do with MOSFET? Well, in my previous video where I discussed the unipolar transistor, I said that this transistor was also called the field effect transistor. I wonder what that has to do with the title of this video. Well, the letters FET stand for field effect transistor. Okay, so that's what we're going to discuss. And as I said in that video, the very first unipolar transistor had a piece of germanium. That's this one. And then there was this little piece of copper right here. Okay, that's because copper is an excellent conductor of electricity. That's what it is. Now, connected to the top of the germanium was a couple of pieces of gold foil. Okay, so what you've got is you got your copper here, your germanium here, and these gold foils. Okay, and gold is an excellent conductor of electricity. So, now, here we have this positively charged carrier layer. That means that there are protons in this layer right here. Okay? Now, if this layer has protons in it, what do you think this germanium had in it? Well, it has electrons. It has more electrons than protons. This layer had more protons than electrons. Okay. So, at this point, I'm going to show you an illustration. You can now see it on the screen. There was a battery connected to the carrier layer, which I'm presuming is the copper, and also connected to the germanium. The positive part of the battery was connected to the carrier layer. The negative part of the battery was connected to the germanium. When the battery was connected to the germanium and the carrier layer, protons in the carrier layer became attracted to the electrons in the germanium. And as we now know, current flowed from the positive terminal of the battery to the carrier layer. And the current flowed from the germanium to the negative terminal of the battery. Why did this happen? When the protons in the carrier layer of the unipolar transistor started flowing towards the electrons of the germanium, molecule holes began to develop in the carrier layer. As far as I understand it, I don't have a perfect understanding of this, protons from the battery flowed into the carrier layer of the transistor to replace the protons that were attracted to the germanium. And if I got any of this information incorrect, please leave me a comment in the comments section below. All right. Again, if I understand this information correctly, the electrons from the germanium were attracted to the protons in the carrier layer. That means the germanium was losing electrons. And if that being the case, then electrons from the battery quickly replaced the electrons of the germanium. Now, if you guys want to elaborate on this, fine. If you will recall from my unipolar transistor video, I stated that two strips of gold foil were connected to the germanium through this carrier layer. And I'm not forgetting about the carrier layer that was placed between the gold foil strips of the germanium. At this point, we have to establish that the first piece of gold foil was connected to the battery. But what about the second gold foil piece? Okay, so we have a battery connected to this side of the equation here, okay? But what about the right? Yeah, this is the left-hand side. Okay, this is the left-hand side of this. So the battery was connected on this left-hand side. But what about the right-hand side? Well, we had another battery connected to the right-hand side. Okay, so you now have two batteries connected to this transistor. But this time, the carrier layer under the gold foil piece was connected to the negative terminal of the second battery. And the germanium under the carrier layer was connected to the positive terminal of the second battery, as you will see on the illustration that you just see right there on your screen. When the germanium and the carrier layer were connected to the second battery, no current flowed at all. Why did this happen? Well, I'm sure somebody in the comment section will clarify this. Okay. There is a tiny space between the two gold foil pieces. When these gold foil pieces were brought close together, protons started to flow from the first carrier layer to the second carrier layer. This caused current to flow from the positive terminal of the battery to the germanium. And this caused current to flow from the carrier layer under the second gold foil piece to the negative terminal of the battery, of the second battery. So now we know the basic configuration of a MOSFET transistor. But this is not the end of the discussion. A MOSFET transistor, a true MOSFET transistor, contains silicon. Okay, that's why they call it a metal oxide semiconductor. Silicon happens to be the 14th element of the periodic table. It has an atomic mass of 28.085. This is the material that's used in the MOSFET transistor. Obviously, silicon, like copper, can conduct electricity, but you have to regulate how much electricity that silicon conducts. If not, then the electrical current can damage or even destroy the MOSFET transistor. That's why the silicon is sandwiched between a conductor, which can be copper, and an all-metal insulator, which can be sulfur. But silicon doesn't conduct electricity as well as copper does, so impurities are injected into the silicon. One of these impurities is called phosphorus. Phosphorus is the 15th element in the periodic table, and it has an atomic mass of 30.97. Do you now see why you have to memorize the periodic table? Now, if you'll recall correctly, I made a video about a term called pentavalent. Okay? Phosphorus happens to be pentavalent. It's a pentavalent material. Okay? Now, if phosphorus is injected into the silicon, then the MOSFET becomes an N-type semiconductor. That's because the silicon and the phosphorus contain more electrons. And this silicon and phosphorus combination becomes the carrier layer for the first transistor. For this transistor, not first transistor, this transistor. But what would happen if you injected the silicon with the impurity known as boron? Boron is the 5th element of the periodic table and has an atomic mass of 10.811. Obviously, this silicon-boron combination would become the carrier layer of this transistor. But you have to keep in mind that this layer would be considered a trivalent layer. And I covered that term in the pentavalent layer video. Okay? So this transistor would be considered a P-type semiconductor. We also know that P-type semiconductors contain lots of protons but very few electrons. That means there are holes in this P-type semiconductor. So what happens if you bring an N-type semiconductor and a P-type semiconductor together? Electrons from the N-type semiconductor immediately flow to the P-type semiconductor and fill the holes that are in the P-type semiconductor. There is a junction where the N-type semiconductor sends electrons to the P-type semiconductor. As the holes near the junction between the N-type semiconductor and the P-type semiconductor are filled, the charges near the junction are depleted. This area near the junction between the N-type semiconductor and the P-type semiconductor is called the depletion region. Of course, that also means lots of current flows from the P-type semiconductor to the N-type semiconductor. But what if we wanted to slow down this process? Well, let's grab us a battery. We will conduct the P-type semiconductor to we're not going to conduct, we're going to connect. We're going to connect the P-type semiconductor to the positive terminal of the battery and the N-type semiconductor to the negative terminal of the battery. The battery will slow down the flow of electrons from the N-type semiconductor. This process of slowing down the flow of electrons and thus the flow of current is called the forward bias. Okay? This process also decreases the size of the depletion layer. But what would happen if we reverse the polarity of the battery? Well, then the depletion layer increases in size and we create a reverse bias. But what is polarity? To understand a polarity, you must understand that a battery has 2 poles. Okay? Now then, I wish I had a battery sitting right here. I'll show you that in an illustration. The first pole is the positive pole. The second pole is the negative pole. Now, one piece of the battery has more electrons than the other piece of the battery. This means that the piece of the battery that has more electrons can be referred to as the negative polarity. Okay, so you have a negative polarity component of the battery because it has more electrons than protons. If a component of a battery has more protons than electrons, then it can be referred to as the positive polarity component of the battery. A lot of fancy terms there, huh? There are two types of MOSFET transistors. The first one is called an enhancement type transistor, and then there is a depletion type transistor. What's the difference between an enhancement type and a depletion type transistor? Before I can fully discuss enhancement and depletion type transistors, I have to introduce another term to you. And this particular term will be covered in greater detail in a future video. It's called a floating gate. An enhancement type transistor is switched off when it doesn't receive voltage from the floating gate. A depletion type transistor, on the other hand, is switched on when it doesn't receive voltage from the floating gate. As you will recall, I covered the topic of voltage in a previous video. So what happens when a floating gate is filled with electrons or protons? Well, directly under the floating gate, there is a trivalent boron and silicon mixed proton filled material. On the left and right sides of this trivalent boron positive filled material, there is a phosphorus and silicon mixed pentavalent electron filled material. Would you like for me to go over that one more time? I'm sure you do. All right. Directly under the floating gate, there is a trivalent boron and silicon mixed proton filled material. That's a big mouthful. On the left and the right sides of this trivalent boron positive filled material, there is a phosphorus and silicon mixed pentavalent electron filled material. I'm sure you've heard all these terms at this point. The protons in the trivalent boron and the silicon mixed material are repelled by the protons that are being ejected into the floating gate. When this happens, electrons from the left pentavalent electron let me say this again. When this happens, electrons from the left pentavalent electron-filled phosphorus and silicon mixed material start flowing to the right pentavalent electron-filled phosphorus and silicon mixed material. This creates what is known as an N-channel transistor. But what happens when you have an enhancement type P-channel transistor? I'll cover this topic as well as the term source and drain when I cover this topic, when I cover the topic of floating gate. But for now, if you want to know more about this topic, watch this video right there, and I have a little hyperlink in the description box of this video. I really appreciate you guys watching this presentation, because I had a lot to say. All right, I will tell you more in a future video, so I'd like for you to stay tuned. Oh, nobody's watching. That's terrible. Okay. Good evening, everyone. It is once again Ted the Speed Learner, and tonight I'm going to cover the topic of the history of XML. But before I do, all right. Now, once upon a time, many years ago, when computers weren't even connected to each other or even to the internet, well, things were radically different. But those days are long forgotten. We have already covered things like the transmission control protocol and some other terms like that in previous videos. So, yeah, all that history's now been covered. So, what is XML? Well, before I begin, I wanted to say I used to type computer code and computer data into a dumb terminal. The actual computer this dumb terminal was connected to was huge. Okay, it actually took up an entire room. So we had a dumb terminal in one room and this great big computer in an adjoining room. And there was a wire that connected my dumb terminal to that computer. When they disconnected that computer, I bet that was hard. I really can't even imagine them hauling that thing out of there. But there was one nice thing about this computer. All the computer programs me and my other classmates were writing were stored on this computer. And all the data files were also stored on this computer. So if we wanted them, all we had to do is tell the computer, hey, pull them up. And it did. There you go. So it was really easy at that time to connect the computer programs we were writing to the data files that were on that computer. All I had to do is say, hey, open up a certain file, find it, and boom, there you go. But much has changed since those days. Now, do you guys recall when I uploaded a whole bunch of HTML videos? I did this years ago. And I informed you back at that time that there was a computer instruction that a computer could use to find specific text in a computer variable. Well, that would be wonderful if you were creating a simple restaurant menu where you're selling just a few food items. In other words, if you're the owner of a food truck and you wanted a simple computer program to keep track of the food you were selling, creating computer variables and using computer code to find information inside computer variables would be a very easy thing to create. And it'd be just as easy to edit. But then we have to think about department stores. Are department stores like food trucks? No, they got hundreds of items. Would you like to declare a whole bunch of variables to represent every single item that you have in your store? Think about it. What if you had a ton of merchandise to keep track of? Well, writing it all in HTML would become a really quick nightmare. And even writing it in JavaScript would be a nightmare at that point. No, you need something with a little more kick. Okay, well, we'll just have this HTML page connect to some kind of Microsoft product. You could do that. Like I tried to do when I tried to install SQL Server into my computer years and years ago. That installation went so badly that I actually had to take my hard drive out, put a new hard drive in my computer, and reinstall everything. You don't want SQL Server, not from Microsoft. You could run it through Microsoft Access, but man, you try to get an HTML page to connect to that. Yeah, wait till you have to make up that connection string. You're going to be like, okay, we don't want that either. But here's the worst part. If you thought that was bad, wait. Because you see, I tried to do all that. You bought the software one time. You didn't have to worry about it. You just installed it, and there you were. Then they came out with Microsoft 365. And guess what? You have to pay a monthly fee to use that stuff now. You want to do that? I don't want to do that. You want to be on the hook for Microsoft the rest of your life? Please. And you don't have to. And you know what the worst part about all of it is? Because a lot of what I'm going to share with you guys tonight, you're going to love this. Microsoft is using it in their software. They have a few little odds and ends that they inject into the dang thing. Most of it's bloatware. But the majority of what they use is stuff that you can get off your own web browser. Amazing, isn't it? Well, fortunately, I found a piece of software that is not nearly as RAM intensive and hard drive intensive as any Microsoft product you'll ever find. And it uses technology similar to what Microsoft does. Okay. And that computer program is called Exist. And if you want to hyperlink to it, I have a video about Exist. You just go into the description box, click it, and you can load it up yourself. You will need Java 11, and I'll explain that in a future video. But I actually did show you guys how to install Java 11. It's not that hard. You install Java 11, you install Exist, and as soon as you do, you're good to go. Now, the best part of Exist is it's free software. Why wouldn't you want it? Okay. Now, in order to use Exist, though, we're going to have to use something called XML, the Extensible Markup Language. Okay. Now, I've been trying to teach you guys XML ever since I put up those HTML lessons all those years ago. Did you pay attention? You should have. XML is the database side of HTML. Okay, and I'm going to explain a lot more about this not too long from now. Now, get this. The languages of XML and HTML are cousins. Can you believe that? So let's take a trip in time back to the 1970s. Now I'm going to introduce you to three people. Now the names of these three people will be down here in the description box below, so you can just look them up for yourself. First one is Charles F. Goldfarb. The second one is Ed Mosher. And the third one is Ray Laurie. Now imagine, if you will, that Charles F. Goldfarb and his friends are wearing hippie clothes and eating at fast food restaurants. It's 1969, and they're working at IBM. They develop a computer language called the Generalized Markup Language. Now, did you notice that the last name of Goldfarb starts with the letter G? Did you notice that the last name of Mosher starts with the letter M? And that the name of Ray Laurie starts with the letter L. The last name starts with the letter L. So when they created this generalized markup language, the G and the M and the L all represented the last names of all three of these guys. Okay, clever, huh? Now, at that time, computers had computer languages like COBOL and Fortran, and they were just starting to have the beginner's all-purpose symbolic instruction code and that kind of thing. Why would you need HTML? Half of these computers weren't even connected to the internet, so you wouldn't need it. Now, if you'll recall, I made videos about the ARPANET. Now, if you're using the ARPANET back in those days, it was very simple and inexpensive to send a text document from one computer to another through a telephone line than to try to connect one database running COBOL or Fortran to another database running COBOL or Fortran across a phone line, okay, with all this extra formatting added on top of it. So we go back to Charles F. Goldfarb, Ed Mosher, and Ray Laurie. They came together. They created a computer language comprised of tags. Tags. Okay. All right. Do you remember when I taught you HTML, all those tags I taught you about? Okay. Do you recall the head, the body, the paragraph, the input, and the form tags? These tags told the computer how to display the text between the opening and closing tags. Okay. So basically what was happening is that you had this web browser, and this web browser contained these tiny little computer programs. And what happened was they took a look at these tags and said, okay, if that thing has a tag, make the text between the opening and closing tags bold, italic, shifted to the left, shifted to the right, etc., etc. Hence the name metadata. Okay, that's going to become important in just a little bit. Now, there was a little problem with the generalized markup language. Back in those days, these tags weren't enclosed in greater than or less than symbols. They just weren't. That's why it wasn't so immediately adopted. But these three computer programmers weren't finished with the project. They started working on a subset of the generalized markup language called the standard generalized markup language. Remember, they still have the GML, but now they're adding this letter S to it. So now we have SGML. Now, this language was comprised of tags that are very similar to the ones you see in HTML and XML both. Now, did you notice that the letter S in SGML stands for the word standardized? Why was this important? Now, do you recall my discussion about the transmission control protocol? Do you recall my discussion about the ARPANET? Not all computers in those days had the same operating system. Not all computers functioned the same way. So these operating systems of these computers had to be upgraded so they could all understand each other, okay? And that they could all understand the instructions from the SGML. Otherwise, no one would have ever used HTML or XML. So they came up with something called the Document Type Definition Program, okay? And this Document Type Definition Program became a part of the SGML computer programming language. This document type definition program determined what kind of document was being processed by various computers. Now, document type definitions were used to parse documents that they were examining. Okay? They say, well, what does it mean by parse? Well, the word parse literally means to break apart. So what they do is they get this little document in, had all these little tags in it, and what they did was they broke it apart, determined what was metadata and what was real data, and then based on the metadata, it would display your real data however you wanted it to display. Okay? So, what would happen is that some computer way off in Timbuktu land would send a text document full of all these HTML tags or XML tags, and of course the data that's inside of them, and they'd send it from one computer to the next. And when the web browser opened, it looked for these tags, determined that the tags themselves were metadata, and would activate little computer programs in the web browser, while at the same time the data between the tags was considered real data, and that was the stuff that was to be displayed in whatever instructions you gave it. Okay? Now, do you recall a guy by the name of Ted Berners-Lee? If you've been watching my videos, you should recall his name immediately. This guy was very familiar with the language of SGML. He based the HTML language on some of the programming that was found, some of the instructions that was found in the SGML. Now, if you didn't want to find and then analyze any data, HTML would have been the last language ever created for computers. But you just want to read raw data all the time on web pages? Of course not. So things like JavaScript and XML were invented. JavaScript was a lot like the C programming language. Okay, so it had a lot of origins with that. Okay, so we now know that HTML was a subset of SGML. But here's the thing. It's a subset of SGML. Okay. Now, why did they just use SGML in the first place? Because SGML is a lot more complicated than HTML or XML combined. It has a lot of instructions, and a lot of us don't ever write those kind of instructions. We really don't, and we never will. So, who worked on this XML project? The list of names is very long, and I won't present all of them here in this video. But if you'll take a look in the description box below, you'll see some of these names, like John Bossack, Tim Bray, and C.M. Spurberg. I guess it's Spurberg McQueen. Okay? All worked on this XML project. The extensible markup language has evolved greatly over the past 20 years. Now, virtually anyone can open an XML document and find out whatever information they're looking for. The implementation of namespaces in XML made it possible for two different XML documents to have identical tags, like title tags or book tags or whatever else. And you could put them all together, and the computer wouldn't be confused as to, well, this is one set of books and this is another set of books. They would know because of namespaces. Now, I will discuss XML documents more extensively in future videos. I also discussed XML in those HTML lessons, so I would take a look at that too. Okay. Well, I want to thank you very, very much for watching this particular video. I will tell you more in a future video, so I'd like for you to stay tuned. All right. Oh, boy. Good evening, everybody. It's once again Ted the Speed Learner, and tonight we are going to cover the topic of the Uniform Resource Identifier. But before I do, now I realize that this video will be very, very short, and that is because I covered in a previous video something called the Uniform Resource Locator. These two are kind of interrelated, okay? So if you already know what a Uniform Resource Locator is, then a Uniform Resource Identifier is not that hard, okay? There's very little difference between the terms. The main difference is that a URI may point to a local database that's running inside your own computer, or it could be pointing to a document you have stored inside your own computer, or it just may not be pointing to anything really at all, okay? Now, obviously, a URI could also be pointing to a document that's stored on the internet. But, like I said, it could be pointing to a database that's on your computer. It could be pointing to just a simple folder on your computer. Or it may not point to anything at all. Now, URIs are often used as XML namespaces, and for good reason. And we will get into that in a future video. So, I would like for you to stay tuned. Good evening, everyone. It is once again Ted the Speed Learner. And tonight, what we're going to do is we're going to cover the topic of bit and byte and the American Standard Code of Information Interchange. Fancy names. They're not fancy topics. Not hardly. Okay. So, now I already went through a discussion of something called a MOSFET, which is a metal oxide semiconductor field effect transistor. Okay. Now, I'm not sure the exact configuration, and we're going to go into it when we do the floating gate video. Okay. But somewhere in there, in this MOSFET, what happens is that electrons are stored in it. Okay. So if those electrons are there and the computer can detect them, then what you actually have is a 0. Okay. Because see, what happens is people are not even told this. No, I'm sorry. If the computer can detect electrons in a MOSFET, it's a 1. If it can't, it's a 0. Okay. That's all simple enough. But here's the thing. They always have to make things just a tad more complicated. Bit, the word bit actually happens to be an acronym. There you are. Bit is actually called a binary digit. Why is it called a binary digit? Well, because 0 and 1. That's all computers understand is zeros and 1. Are there electrons in a MOSFET or are they not there? Okay. Now, you have to understand that in the early days of mathematics, when they actually declared there was such a thing as 0, what did they call 0? They called the absence of value. So, if we're to go by computer terms, when there's no electrons in the MOSFET, that's a 0, people. That's the absence of value. That means there is nothing there. Okay. Now, as I said, this is the only language that a computer truly understands. So how do we communicate with a computer? Well, when modern day computers were first invented, a computer term was developed. And of course, that computer term was bit. And I just told you that's an acronym for binary digit. Okay. So now you know why there's a 0 bit and a 1 bit. But this doesn't solve our problem. How do humans communicate with computers? At this point, you would never guess that a guy by the name of Samuel Morse would play a role in the way humans communicate with computers. Let's think about this. Didn't Samuel Morse develop something called Morse code? Well, of course he did. At this point, you may have realized that Morse code was transmitted by electrical signals. That meant that they were sending electrons through a wire, and the current was coming back on the other side. So if you sent electrons out, the current came back. If you were drawing in electrons, then the current went forward. Get the idea? That's why they had all those electrical lines back when they had the Morse code. Now, I do want to mention briefly that I fully plan to teach you guys Morse code on this YouTube channel very, very soon because I'm running out of cursive letters, so we got to teach you something. Okay? All right. Now, if you guys watched my videos about watt, amp, and volt, you would know about the, and I'll show it to you again just one more time. Okay. So let's pretend we have this wire. There's your wire. Your electrons are moving this way, and your current is moving this way. If this gets reversed, then the current would be moving this way, and the electrons moving that way. See in the picture? Okay. So all this should sound very familiar to you. But the person who should receive the most credit for the creating of this language, which this binary language, which would allow people to talk to computers, well, this guy's name is Bob Beamer. And his name will be in the description box of this video. Okay. he had to base his work on the computer term byte. Okay. Now, a byte is, believe it or not, 8 bits. So, believe it or not, you see 8 bits here. Okay. That 8 bits creates a byte. This whole thing, all these zeros and ones together, there's 8 of them. They create something called a byte. Okay. Now, just one problem with all this. There are 2 conflicting stories about how bytes were created because we have 2 different people working on the same thing at the same time. Now, we have the first guy, and his name is Werner Buchholz, and if I mispronounce that name, please forgive me, and Louis G. Dooley. And if I mispronounce anything, please leave me a comment in the comment section below, and I want to thank you very much for clarifying things for me. But let's go back to Mr. Werner Buchholz, I guess. Now, what he did was he grouped 6 bits together to form a byte. But Bob Beamer, he grouped 7 bits together to form a byte. Okay. Now, Bob Beamer, he took his byte information and sent it to the International Business Machine Corporation. Okay. Okay, correction. He didn't send it to IBM. He was working for IBM, and he sent it to a place called the American Standards Association in 1961. Okay. So we have Bob Beamer. He groups his bytes by 7 bits. And what he does is he sends them. I'm blowing this. Good evening, everyone. It is once again Ted the Speed Learner, and tonight I'm going to cover the topics of bit and byte and the American Standard Code of Information Interchange. But before I do, now, recently I've been discussing transistors and electrons and protons and electrical current and so on and so forth. I actually discussed the topic of MOSFET, which is a metal oxide semiconductor field effect transistor. In a future video, I'm going to discuss something called the floating gate. Now, the floating gate is a component of MOSFET, and I can't tell you that I understand the whole thing correct, all of it, okay? I understand quite a bit of it, but I don't understand everything, okay? Now, there are electrons that get stored in the floating gate, okay? Now, if a computer can detect that there are electrons being stored in the floating gate, it calls that a 1. If the computer cannot detect the electrons in the floating gate, that's a 0. Okay? Because you see, these are what is called binary digits. Okay? That's what bit is actually an acronym. The word bit is an actual acronym standing for binary digit. And there are 2 binary digits. There's the 1 here, and then there's the 0. Now, if you'll remember from mathematics, I discussed this in an earlier video, where in mathematics, when they came up with the concept of 0, that was called the absence of value. And it had no value at all. And let me tell you something: when you have a floating gate and there's no electrons in it, it's not valuable to a computer at all. There you go. All right. So now we understand this. Now, the language of bits is the only language that any computer will ever understand, period. Okay? So how do humans like us communicate with these computers? Well, at this point, you probably would never guess that a guy by the name of Samuel Morse would play a role in all this. Say, what does Samuel Morse have to do with computers? But this might look familiar to you. There's a computer wire. Well, that's not even a computer wire. That's like those wires from the telegraph office. Electrons would move one way and current would move the other way. And if you reverse this, the current would move this way and the electrons would move that way. And that's how Morse code worked. Not that you wouldn't have Morse code. And as a side note, I will be covering the topic of Morse code in a future video. Yes, I'm going to teach you all the little dots and dashes because I'm running out of cursive letters and I need something else to teach you guys. So what the heck? Anyway. Whoa, almost turn the camera off. Whoops, shouldn't do that. Now, Morse code works on the property of electrons. The electrons are there or they're not. Same thing with MOSFET transistors. Either there are electrons that the computer can detect in the MOSFET or it can't. There you go. You got zeros and ones. So, who do we credit with the creation of bits? Well, there's two conflicting stories about that. The first one involves a guy by the name of Werner Boltschulz, and his name is down here in the description box below. And the other one is Louis B. Dooley. Now, Werner Boltschulz grouped 6 bits together to form something called a byte. Today, this row of 8 zeros and ones would be considered a byte. Back in those days, Werner Boltschulz subtracted 2 of these digits and called that a byte. But here's the problem. About that same time, there was this guy named Louis G. Dooley, and his bytes were 4 bits long. So you have Mr. Dooley, his 4 bits, and we have Mr. Boltschulz and his 6 bits. Neither one worked. So we have this third guy, he steps in, and his name is Bob Beamer. Originally, he adopted the 6-bit definition of a byte, and he created a computer standard that he submitted to the American Standards Association back in 1961 because he was working at the time for IBM. In 1963, which was 2 years later, the American Standards Association finally published a document called the American Standard Code for Information Interchange. It was based on a grouping of 7 computer bits. This document would eventually be called the ASCII. This document presented byte translations for every letter of the English alphabet, both capital letters and lowercase, all the digits 0 through 9, and a lot of punctuation marks. Okay? Finally, people could communicate with computers effectively. Now then, you say, well, how does this ASCII work? Okay. Well, let me tell you how this works. You have 8 bits here, all zeros. Okay. Now, what if you change this 0 to a 1? Well, then what you'd have is a value of 1. So you'd have a byte 1. Okay. And that would represent, I don't know, you have to look on the chart, the ASCII chart. If the first one on that chart is this one. Okay. Now, what would happen if we change the last 2 digits? So now we have 1 here and a 1 there. Here's the thing. This is the 2 column. So now you'd have 2 plus 1 equals 3. There you go. So you'd have a chart. So this goes on and on. So what you would have is you'd have a 1 column, a 2 column, a 4 column, an 8 column, a 16 column, a 32 column, a 64 column, and let's see if I remember right. Let me calculate this. 64 times 2. Yep, I was right. 128. So like I said, you'd have this column, this column, this column, this column, this column, this one, and this one. So you have your 0, 0, 0, 0, 0, 0, 0, and 0. Okay, so for all zeros, that's going to be called the null. There's nothing there. Okay, but let's say we change this 0 here to a 1. So what we do is add 1 to all these zeros, okay? But we're not really adding 1 here. We're adding 8, okay? Now, we don't add a 4, we don't add a 2, we don't add a 1, we don't add all these because there are zeros here, okay? So let's say there was a 1 here. So if you have a 1 under the 8, you have a 1 under the 2, then it would be 8 plus 2, which would equal 10. So the 10th character of ASCII would be represented that way. And that's how that works. Okay. So eventually the ASCII started converting letters, numbers, English language punctuation, and even special symbols into 8-bit combinations, which I just illustrated to you. That's why we have the current term byte. Now, there's only one other thing I want you to notice. You often see when you deal with computers, especially with internet, okay? If you're dealing with computers, you'll probably see terms like MB, GB, and of course, TB, megabyte, gigabyte, terabyte. But you got to watch out for this. When it comes to internet companies, what you'll see is an M lowercase b, a G lowercase b, and a T lowercase b. Like, what does that represent? Lowercase b always represents bit. And so therefore, when you're thinking all these bytes are going through the computer or through the internet and getting to the other side, not really bytes, they're bits. All your internet's measured in bits, not bytes. So it's actually going 8 times slower than what you think it is. That could be bad. All right. So hopefully now you understand what's going on with computers. And I will tell you more in a future video, so I'd like for you to stay tuned. Anybody else? Again, no. Okay. All right. Let's go on. Good evening, everybody. It's once again Ted the Speed Learner, and tonight, what we're going to cover tonight is the EM dash. Okay, and there is a difference between the EM dash and the EN dash. That's because the EM dash is actually longer than the EN dash. Okay, but before I cover all this, all right, let's go on here. So, what is the big deal about the EM dash? And in order to understand why the EM dash is so important, we have to dive into printing history. The first printing press was comprised of metal letters created by cast molds. These letters would have to be placed individually on a printing press in a backwards order. That was indeed a cumbersome task. But the task became even more cumbersome when you considered what happened when the text was printed. All the metal letters had to be removed from the printing press and returned to the boxes that they were stored in. Well, this all changed when there was a guy by the name of Ottmar Mergenthaler, I guess. If I mispronounced it, please forgive me. This guy here, and his name will be in the description box below, he created something called the linotype machine. This machine had a component that would release a mold for every letter that an operator typed. Once the molds were placed together, liquid metal was poured into the molds. This invention would eventually lead to the creation of the EM dash. I have a web article. It's down here in the description box below. Now, no one knows for certain when the first EM dash was used, but we do know that the EM dash had to be the same length as the capital letter M. That's right. So EM, the M in it stood for the length of the EM dash. So now that we know some history about the EM dash, we need to know how to use the EM dash. Well, if you need to create a pause in your text, feel free to use the EM dash. That's because the EM dash is stronger than the comma, but not as strong as the period. Can this dash be used in other ways? Well, of course it can. An EM dash can also be used to replace a parentheses, and it also has other uses you can research for yourself. But how do you create an EM dash? Well, you could use a word processor, or you could use a very special HTML code. It's from the Unicode 8, okay? And we'll get into that in a future video, probably tonight, okay? So, they have a key. I'm going to show you this. To create the EM dash, you're going to use the ampersand, okay? M D A S H, just like that. That's from Unicode, and I'll explain Unicode in a future video. Okay. Or you can discover some other fancy way to create an EM dash, because there's plenty of ways to do it. All right. That's all I got for you for this particular video. I'd like for you to stay tuned for yet another video. Are we learning yet? Oh, I see. Oh. Stalzy randomly had this pop up on my YouTube recommended. Oh, well, I'm glad it did. I'm glad you're watching. I'm sure you're going to learn a lot if you stay here long enough. And I want you to. I want you to learn all this because there's a lot of stuff that needs to be taught to you. Okay. Let's get ready. Oh, I got to turn this on. There we go. Good evening, everyone. It is once again Ted the Speed Learner, and tonight I'm going to teach you something called lattice multiplication. I'm sure you've never heard of it before, and if you have, that's great. But if you have not, let me teach it to you. Because if you don't have a calculator, this could become real handy real quick. Okay? But before I get started, all right, so what is the origin of this type of multiplication? Let's take a little time machine and let's go back to the country of Italy. This method of multiplication in Italy is called gelosia. But what does this mathematical method have to do with jealousy? Well, if you're bringing up the topic of human relationships, then gelosia actually does mean jealousy. But the word gelosia in Italian also means a window shutter. So what is a window shutter? Well, shutters are actually items you can add to windows that can enhance the privacy of your home as well as block strong winds from damaging your windows. So what you do is you close the shutter and then you lower the window and lock it, and when a storm came through, it would tear up the shutters and not the window. Does this mean that the people of Italy created this mathematical method of multiplication? Well, no. If you research the topic further, you find that it was someone in India that created this mathematical method. No one is exactly sure who it was that in India that invented this method of mathematics. But someone in the country of China read some of the ancient texts of India and published their own findings in textbooks. At some point, people from Italy traveled to China and read their textbooks, and now we have this method of multiplication. So, how do we use lattice multiplication? Well, let me ask you something. Doesn't this look like a window? I bet it does. Let's multiply some numbers. We're going to multiply 43 by 32. Now, if we were to use the traditional way of doing this, which this is what I was taught in school, we'd have 43 times 32, and then we'd have to multiply the 2 by the 3, and we get 6, and of course we have to multiply the 4 by the 2, and we get 8, and what would make it worse is if you had to, then we have a 0 down here, I think. Then you have 9 here, and of course you have 12. If you multiplied the 3 and the 2 like this, and let's say you had bigger numbers here, and it generated, like, say, an answer of 10 or 12 or 15 or whatever, you'd have to carry the 1. Talk about messy, okay? Then you have to total up at 6 and 9, and that's 17 there. Carry the 1, that's 3, and I think we're going to get a result of 1376 if I recall correctly. But why go through all that hassle? Let's see if my math is correct. Let's draw some diagonal lines. See those diagonal lines? Okay, so we're going to have we got 3 times 2, and that's 6 there. 3 times 3, that's 9 there. Then we got 4 times 3, and that's 12 there. We got 4 times 2, and that's 8 there. So now we got the 6. And, of course, 9 and 8 is 17. Going to have a 1 there. And 2 plus 1, of course, is 3. And, of course, you have the 1 here. So your numbers here, 1, 3, 7, 6, happens to be this one right here. And there's your answer. So I'll explain it again. 3 times 2 is the 6 here. 3 times 3 is the 9. 4 times 3 is the 12. 4 times 2 is the 8. Then we add this column up, and that's 6. And 9 plus 8 equals 17, but we got to carry the 1. And we put the 1 up here. Plus 2, that's 3. That's this 3 right here. And this final column, we didn't have to add anything, so there's your 1. And that is how lattice multiplication works. You are more than welcome to research this on your own. I hope you learned a lot. I will tell you more in a future video, so I'd like for you to stay tuned. What does the EM dash look like? Okay. Glad you asked. I will definitely draw this out when I make this a separate video, because what I'm doing is I'm recording the audio versions of all the videos I'm going to put up later on. But an EM dash would look like a giant line like this, okay? Then you have the EN dash, which is smaller, and the EM dash, which is bigger, okay? And that's what you'd have. And you are more than welcome to research EM dashes and EN dashes, and you can learn all this stuff. I welcome you to do it because you'll learn a lot. But anyway, let's go on, shall we? Good evening, everyone. It is once again Ted, the Speed Learner, and tonight we're going to be covering the topic of negative numbers. But before we do, okay, so we're going to return back to the 1st century, okay? And I'm sure you guys, if you know anything about biblical text, you know about the story of Jesus of Nazareth, okay? Matter of fact, yes, that is where the hard rock band Nazareth got their name. Okay. Now, back in those, mathematical experts like Euclid refused to cover the topic of negative numbers. Of course, then again, they didn't cover the topic of 0 either, so there you go. After all, they used numbers to measure land and homes and other physical objects. Well, if you were measuring things, there is no such thing as a 0 land, and there's definitely no such thing as a 0. There's no negative land. There's no 0 land. There you go. Why would they need numbers that didn't measure anything? Not practical. So they considered the topic to be absurd. But 700 years later, there was a mathematical genius, and I'm going to leave his name down here because I simply cannot pronounce it. He started a discussion about profit and debt. Now you needed negative numbers, okay? Debt was represented by negative stuff. So now they had a reason to cover negative numbers. So at this point, we're going to be covering the topics of negative addition, negative subtraction, negative multiplication, and negative division. Now, negative addition is pretty easy to understand. Basically, you're going to have 2 add-ins. Okay? We're going to make the first one positive. And then we're going to make the second one negative. How do we solve that? That's easy. What we're going to do is we're going to change the plus sign to a minus sign. Change the plus sign to a minus sign. All right. Now, what if you had a situation where the first add-in is -5 and the second add-in is 3? Okay, we'll just reverse the numbers. So what we're going to do is we're going to say 3 minus, okay, just minus 5. And 3 minus 5 is -2. Okay. Now, what would happen if both add-ins are negative? So let's say we have -5 plus -3. Well, -5 plus -3 is just going to be -8. And you don't have to say -5 minus 3 is -8. That's silly. Okay. Now, what about negative subtraction? Well, let's start with this problem, this subtraction problem with a menu end, and it's positive. Now we're going to subtract a negative subtrahend. Okay. Now, if you do that, all you have to do is change this to a plus sign, remove that negative there, like that, and that makes 8. But what happens if your minuend and your subtrahend are negative? Okay. So you have -12 minus -6. What we're going to do is going to change this like this and get rid of that. So now we have -12 plus 6 equaling -6. Just like that. Sounds simple enough, huh? But it gets worse. Okay. What about multiplication? Let's return to the mathematics of the guy that we had down below. He postulated that numbers multiplied he postulated that numbers that were multiplied were just numbers added to themselves a certain number of times. So let's say you have 2 times 2. We already know that's going to be 4. Okay. So we have the multiplier 2 multiplied by the multiplicand 2, and it equals 4. All right. Well, he also stated that 2 plus 2 equals 4, which of course is true. Now, he takes us one step further. He says, okay, well, what if you have 2 times 3? Times 3. We know that's 6. But according to him, you'd have 2 plus 2 plus 2, because you had 2 3 times. That made your 6. This led to a problem. what if you had 1 times 1 equals 1? Now, if we were to go strictly by this guy's math, then we could also say 1 plus 1 equals 1, which, of course, right now we know that's not true. So what's the flaw? Well, so we're going to change his little instructions really quick. So again, we have 1 times 1 equals 1, which is true. Now we're going to have 1 plus 0 equals 1. That's how you change that. So it's one number of times. Okay? And then you'd have the correct answer. So how does this theory affect negative multiplication? Well, let's try another math problem. Again, we're going to have a multiplier. And it's going to be 2. Okay? Now, let's multiply that times negative 2. Well, what we're going to say now is 0 plus negative 2 plus negative 2 equals negative 4. Okay? So we're going to start out with 0, and we're going to add the negative 2 and the negative 2 together because it's 2 times, and that's how you get your negative 4. And that's how he wanted. That's not how he wants you to think of it, but he wants you. Everybody else wants you to think that way too. Now, what if the multiplier and the multiplicand of the math problem? What if they're both negative? What's going to happen with the product? Well, let's take a long walk down the yellow brick road. All right. First, we're going to have a negative multiplier. Then we're going to have a negative multiplicand. So, but let's visualize this multiplier a little more carefully. We can say, group this, negative 1 times 2, then times negative 2. So now we can say it like this. Okay. Because negative 1 times 2 actually gives you negative 2. So we're going to separate this out. But we already know that if you have numbers that are multiplied together like this, you can multiply them in any order. So now we're going to shift things over. We're going to have negative 1 times negative 1 times 2 times negative 2. Now, you'll love this. So we're going to take one step further. So now we got this. But this gets more fancy. You're like, now what are we going to do? Right. Hope you wrote all that stuff down. If you didn't, pause the video and write it all down. Now we already know that we have the negative 1 over here. Okay. Oops. And we have it multiplied by negative 4. Why? Because 0 plus -2 plus -2, of course, is -4. Well, -1 times -4 is going to be 4. But if you thought that was easy, oh boy, I got more for you. What happens if you have a division problem and either your divisor or dividend is negative? I regret to say that there's little documentation to indicate the history of division, especially when it comes to negative division. But the rules of multiplication can be used to solve these division problems. If either a divisor or dividend of a division problem is negative, then the quotient will automatically be negative. So if your divisor is negative, your quotient is going to be negative. If your dividend is negative, your quotient is going to be negative. And if the divisor and the dividend is negative, your quotient will be positive. Okay? And you can look this up in the article below. Okay? All right. Well, I want to thank you very much for watching this particular presentation. I will tell you more in a future video, so I'd like for you to stay tuned. Are we learning something here? I hope you are. All right, I'm going to take a quick potty break, and I'll be right back. Right back. Whoa. And we go on. Good evening, everyone. It is once again Ted the Speed Learner, and tonight we're going to be covering the topic of imaginary numbers. Now, before I could... that was terrible. Good evening, everybody. It is once again Ted the Speed Learner, and tonight I'm going to cover the topic of imaginary numbers. But before I start, okay, as I stated in my video about negative numbers, math experts like Euclid didn't consider negative numbers real numbers. That became a problem. They called these numbers absurd, and for a good reason. But hundreds of years later, the attitude of various civilizations changed due to the accumulation of debt. In their eyes, debt should always be represented by negative numbers. You would think that the change of attitude towards negative numbers would fix everything that was problematic in mathematics. Of course, you'd be incorrect. What about the square root of -1? Who solved this problem? Well, let me introduce you to a guy. He was a ballistics expert, and his name was Niccolo Tartaglia. Niccolo Tartaglia. His name will be in the description box of this video. He noticed that multiplying negative numbers always produced a positive result. That became a problem for him because he was trying to solve quadratic and cubic math problems. So I decided to label the square root of negative 1 as I. So anytime you see you ever see the square root of negative 1, it's automatically an I. And from that day forward, if you need the square root of any negative number, you would multiply that number by the lowercase letter I. And that's it. Alrighty. If you want to do more research on that, I highly recommend you do so. I will tell you more in a future video, so I'd like for you to stay tuned. Good evening, everyone. It is once again Ted the Speed Learner, and tonight I'm going to be covering the topic of number or pound sign. Okay, and it looks just like this. But before I cover this topic, okay. So what is a number or pound sign? No historian is exactly sure how the pound sign was created. Some people have suggested that the pound sign was created in the Roman Empire, and it was an abbreviation for the Latin words libra pondo. The word libra usually meant a pair of scales. Okay, this led to words like liberation. This would represent some kind of a weight or weight measure. The word pondo, on the other hand, actually means pound. So if you had a pondo, you actually had a physical pound. Okay. So is the combination of these letters, is the combination of the letters LB the origin of the pound sign? Well, depends on who you ask. There are others who claim that this was actually the number sign and it was conflated with the sterling pound sign during the advent of the telegraph. I'll let you research that topic at your earliest leisure. Where is the pound sign and how should you use it? If you look above the number 3 on your keyboard, you will see the pound sign. That means you will have to hold down the shift key to print the sign in your word processor. If you have a keypad telephone, you will find the pound sign underneath the number 9. The symbol can represent a number. Okay. Now, you remember when you owned those number 2 pencils? Okay. It can represent a weight measurement. Okay. You can actually have the pound sign when you have 2 pounds of sugar. You'll see that in recipes. In computer addresses, it can also be called a hashtag. You've seen that a lot, especially in X, which was originally known as Twitter. And you can see that on YouTube. You can see it, you get the idea. Okay. And this number or pound sign can actually be a part of a web address. Now, if you could think of any other uses for the pound sign or the number sign, please leave them down here in the comment section below. I will tell you more in a future video, so I'd like for you to stay tuned. Okay. Here we go. Good evening, everyone. I'm going to cover the mathematical term of absolute value in this particular video. And before I do, though, all right, so what is absolute value? Well, this is going to be easy. It's all based on a number line. Okay, so let's draw a number line, shall we? Then I'll show you what the absolute value symbol looks like. Okay, there's your typical number line. Now, before we get into this, I wanted to say there is much debate as to who formulated the idea of a number line and who formulated the idea of absolute value. I could spend lots of time here discussing this topic, but I decided to make this video very, very simple. If you want to look that information up, you can go ahead and leave your research right down here in the comment section of the video below. Now, as you can see, modern day number lines contain both positive and negative values. It also contains the absence of value, which I discussed in a previous video. Yes, 0 is the absence of value. If you want to consult all that, you can do some research on that yourself. But this wasn't always the case. As I stated in my negative number video, some people decided that the idea of negative numbers was just absurd. So imagine if all your number lines just had positive numbers instead of negative, okay? So until people started calculating debt, no one considered the idea of negative numbers. Because of this, a number line consisted only of positive numbers, okay? So they would say, well, the number 0, or the absence of value, was the beginning of the number line. It would just go this way, okay? So at this point, you were trying to figure out the distance between the number you had. Let's say you had a number 3, okay? So we'll just put down here 3. You had to figure out the distance 3 is from 0, okay? So you go 3 points to the left, okay? That's the distance. Well, as you know, distances don't have negative values. So if you ever see the absolute value of 3, the absolute value of 3, indicated by these parallel lines, is 3. Now, what if the number is negative 3? Doesn't matter, because the absolute value of negative 3 is 3, because even though you're going backwards on the number line, you're still going a distance. There are no such thing as negative distances, so there you go. All right. And that concludes my video. I want to thank you very much for watching this video. I will tell you more in a future video, so I'd like for you to stay tuned. Okay. Good evening, everybody. It's once again Ted the Speed Learner, and tonight I'm going to cover the topic of cross multiplication. And before I do, okay, let's get into this. There are plenty of websites that show you how to cross multiply fractions, but feel free to attempt to find any history about cross multiplication, because there isn't any. I looked. Now, I do know for a fact that Euclid covered the topic of ratios in his Elements books. That's Euclid Book 10. And I have videos about this topic on my YouTube channel. Yes, I covered Euclid Book 10. However, unless someone contacts me with a valid website that details the history of cross multiplication, I just won't cover its history here. As for how to cross multiply, it's really very simple. Okay? The first thing you need is a ratio. Okay? Now, there's a ratio. 2/3 equals 4/6. All right. If you divide the numerator on the left side of the equation with the denominator on the left side of the equation, you will obtain the same quotient as you would by dividing the numerator on the right side of the equation with the denominator on the right side of the equation. So 2/3 is roughly 0.66. And the same thing is true over here. divide by 4 by 6, you get 0.66, whatever, okay? Because believe it or not, yeah. Okay, so we now know that if you divide 2 by 3, you get 0.66. You divide 4 by 6, you get 0.66. Since you know that, we'll take this off like this. We can now cross multiply. All right. Now, we're going to multiply this numerator by this denominator. Well, 6 times 2 is 12. And we're going to multiply this numerator by this denominator by this numerator, and we're going to get, and there you go, 12 equals 12. Simple as that. Now, if you're trying to calculate ratios, and those ratios contain variables, this technique will be very handy to you. I hope you appreciate it. All right. I will tell you more in a future video, so I'd like for you to stay tuned. Good evening, everyone. It is once again Ted the Speed Learner, and tonight we're going to be covering something called the tilde. But before I do, okay, let's get into this, shall we? In ancient times, there were no printing presses. Many civilizations used to hire scribes just to print text, and these scribes would use inkwells, and they used sheets of papyrus. Obviously, it was expensive to hire a scribe to print your thoughts on sheets of papyrus. So abbreviating words would allow you to add text to your document and yet save you some money. This was the primary reason alphabetical characters like the tilde were invented. But if you speak, read, or write fluent Spanish, you will see this mark over the letter N. This mark indicates the proper pronunciation of the letter N in Spanish. Okay. So what's the mark look like? Well, looks like that. But you will also find this mark in mathematical equations as well as in computer programs and even in website addresses. If you find this mark in any of your mathematical equations or any computer code, feel free to tell me all about it in the comment section below. All right. I will tell you more in a future video, so I'd like for you to stay tuned. All right. Still nobody. Okay, that's fine with me. Good evening, everybody. It is once again Ted the Speed Learner, and I know you're saying, wait a minute. After HTML lesson number 77, you went silent for a long time. Well, part of it was due to the fact that I'm in a bedroom and it's hot, and let me tell you something, it's just really nice when I don't have to speak and you guys can still learn something. But in this particular case, I felt like it was very necessary to get back on the air with these things because of the complex material I'm getting ready to cover. Okay, it's very, very important. I have been working on this project for some time now, and I will explain some of the complications of this project at the end of the video. So I would like for you to continue watching all the way through so you can find out, number one, why it took me so long to make this video, and number two, some of the problems I encountered while I was doing it. All right, so let's go over HTML lesson 159. Yes, I will finally publish the code of this program onto my Facebook fan page, so I'd like for you to take a look at it. All right, so here we go. Now then, oh dear. Let me make sure everything is going kosher. Ah, there I am. Okay, nobody's watching. That's good. All right, let's go. All right. Now, for those of you who are not watching, I mean, you're seeing this code on the computer screen. All right. Now, your HTML tag has to contain namespaces, and I'm still working on these namespaces because what's happening here is that they have gone into something called HTML5, and because of this, you have to isolate your SVG code from the rest of your code. Okay, and this requires namespaces, and that's why I have an XML namespace. See, the thing is that as you're looking at this code, and I'm going to briefly bring you back here, might have just pointed out, I don't know, but you'll have XMLNS. See that XMLNS? And then you'll have this colon, and then you'll have this SVG. Okay? SVG has to be part of its own namespace. See that? Okay. So really what you got on this SVG Bezier curve web page is I'm not doing this right. I am really not doing this right. Good evening, everybody. It is once again Ted the Speed Learner, and this is HTML lesson number 159. And I know there's going to be a lot of things you guys are going to say. First thing you're going to do is you're going to watch this whole video, and you're going to say, well, this isn't the Bezier curve. Well, this is the foundation for the Bezier curve. I'm putting a foundation so that the next time I come on here, I will cover some other letters, okay? Now, the Bezier curve is not represented by the letter A. It is actually represented by the letter Q or C, and I'll explain that later in this video. But there's a couple other questions you guys are going to be asking. One of them is, why is this Bezier curve so important? This is why it's so important. See this soup can? That's why it's so important. If you're going to try to draw this, you're going to need it, okay? But the third question you're going to ask me is, well, you never really had any sound on these HTML lessons after lesson number 77. Now you got sound again? Why? Because this is that important. If it wasn't this important, I wouldn't have any sound. Okay? But the other question is, what took you so long to do this? What took me this long to do this? Well, I ran into a bunch of complications. And I will explain those complications later on in this video. If you stay around and stick around long enough, you'll understand what's been going on. All right. So all the computer code for this particular video will be placed in the on my Facebook fan page, so you can just copy it and paste it, whatever. Another question you guys are going to be asking me is, why am I not putting my typical intro into this thing? Well, that's because this topic is way too important. And I seriously doubt a lot of people will watch this until they realize just how important this thing is. And by that time, they'll have watched all my other videos and therefore. So let's just go into this, shall we? All right, what you're seeing on the screen right now is the HTML code of this particular project. You will notice namespaces. See, the letters XML and S stands for our XML namespace, okay? I had to have a separate SVG namespace because SVG has to be under a very specific namespace. or it won't work. So we have to separate the SVG code from everything else. Isn't that fun? That's why I have multiple namespaces in my HTML declaration. Okay? And yes, we will eventually validate this project. One of the things I want to tell you about that is that I've been having problems validating this project, and I'll explain that at the end of my video. And when I get that all fixed up in a future video, I will go ahead and present that. All right. So in this particular web project, we're going to have a title to this project. It's going to be linked to a CSS page. In this particular case, you probably don't really need it. And I doubt that I'll even show you the CSS in this video, but I'll go ahead and show it to you in the next one. You're going to definitely need a script tag because you're going to have to use JavaScript to access your database because you're going to need it. And then you're going to have a body tag because you're going to run a function right off the bat. Okay, that's why they have the onload event. Okay, you're going to have a button at the top of the screen which you can click, and I'll show you why to do that in just a second. Then you're going to have an SVG tag and two path tags. And that's because you're going to be drawing not one arc, but two. Okay. Now, why are the arcs so important? Well, it's all based on the soup can. When you look at it up front, do you see the entire top of this can? Of course not. You don't. So you need an arc up here and an arc down here that are exactly the same size. That's why this video is so important, because without that, you can't draw things like soup cans and other projects which you really need to draw. Think about it. I'm going to illustrate this to you. Take a look at this car. You see that area where the wheel is? That front is exactly the same size as the back. In order to achieve that, you have to know how to draw these curves and make them exactly the same size. That's what you have to do. And I'll explain that in this video. All right, so in this particular video, normally I would show you the cascading style sheet, but it really isn't necessary. So let's go ahead and open this up. And we're going to go ahead and open this up. All right. Now, in this particular project, we're going to have two functions. Okay? We can call them anything. The first function is going to have 6 variables, 6 of them. Okay? Now, it's going to become important to make sure, and I'll tell you this because I ran into a ton of problems with this thing. You want to make sure your variables are getting correct values. Okay? I'll explain this to you. So we're going to have a statement. It's called document get element by ID. And I'm going to actually flash up here. I know I've got it here on my dry erase board, but I'm going to actually flash it up here. What you're going to do is you're going to say, what you're going to do is you're going to, let me try to explain a little more slowly here. You're going to add a text box to your web page. Okay. Now, eventually you're going to delete that that text box off your web page. Okay. The only reason why it's going to be there for a while is because you have to see if those variables are getting those values like they're supposed to. So you're going to use the statement document get element by document get element by ID, and then you'll access your text box, and you'll change the value inside your text box to whatever the variable value is. And that's how you'll do that. Okay. Now, you'll notice that I have two variables here. They're both called attribute name. Okay. One's called attribute name, and the other one's called attribute name 2. Okay. Because you're going to be changing some attributes on this thing. You have elements and then you have attributes. Okay. And you're going to be changing some of these attributes, and for good reason. Okay. So you have to tell the computer what attribute you're going to change. Now, what's the letter D represent in this case? Well, the D represents, it's kind of a drawing thing. It says, draw this particular object. Okay. And if you want to look at it more precisely, you can go ahead and do that. Fine. Okay. The other one is style. What does that mean? Style refers back to cascading style sheets. Okay. Now, you're going to see properties. Okay. Because when you're changing how an object looks, that's a property. Because you have these objects, you have their properties, you have their methods. Well, these particular objects are not going to be doing anything. They're just going to appear differently because you're changing the properties of them. Okay, remember how I had a video about objects, properties, and methods being like nouns, adjectives, and verbs? Same deal. Okay. So, we want this arc to be a blue arc. Okay. We don't want the width of the arc to be great big. So we had it small, 3. Okay. And we don't want anything inside the arc to be filled up with anything. Okay. Now, what about the M? Okay, we're looking at coordinate now. What about the M? Well, I'm going to tell you what the M is all about. The M has these X and Y coordinates. And what it's saying is, I want you to move the cursor to these certain X and Y coordinates. And that's what the computer will do. Not drawing anything yet, but it is actually moving the cursor to a certain point. Okay. Now, what about the A? The A represents the word arc. But what about those numbers? Are those coordinates? Oh, no, they're not. They're radii measurements. Okay. Ever heard the word radius? Okay. You have more than one radius. You have an x-axis radius and a y-axis radius on this thing. Okay. So that's the measure of the radius. Now, what about those last coordinates? Well, the last ones are x and y coordinates. Now, as I said, the 375 and the 200 are x and y. Boy, that's terrible. They're coordinates. Okay, so you've told the cursor with the move to statement, move to coordinate 375, 200. Okay. Now, the other one underneath is 475 and 200. So, basically what you got here is 100 pixels. You got 100 pixels between the beginning coordinate and the ending one. This is important. Okay. And here's the reason why. Because what you actually have, and I'm going to draw this out for you, and this is the secret to the whole thing. Let's imagine that there are two guys. Okay, you got guy number 1 over here. You got guy number 2 over here. Now, let's say that there are, I don't know, 100 centimeters apart. Okay. This guy is 100 centimeters away from this guy. That means that this guy is only 50 centimeters from this flagpole. This would normally be a flagpole. We'll just put a little flag right there. Okay, so you got your flagpole here. He's only 50 centimeters from the flagpole, and this guy's also 50 centimeters from the flagpole. This is where you get your arc measurements of 50, okay, and 50. Okay, but it's not really 50 here and 50 here. Okay. The first measurement is this measurement from here to here. The second measurement is from here to here. Okay. So you got a little ball right here, and it's 50 centimeters from the ground. So this guy is 50 centimeters from the flagpole, and the ball is 50 centimeters from the ground. This is one radii. This is the other. Are you getting it yet? I'm glad you are. Okay, so now we understand this. Now, what are we doing with the variable button identification? Well, what we're doing is we're storing an object inside that variable. So that variable is now going to become an object. And we do this with document get element by ID, Bezier curve button, right like that. All right. Now remember, you now have an object inside the button identification variable. So now you can change the style properties on this button. Okay, because now your button identification is an object. Now you're going to change its style properties. You're going to tell the button to be positioned 50 pixels from the top of the screen. You're going to tell it to be 350 pixels from the left of the screen, and you're going to tell it that the button has to be 50 pixels high. Okay, so the distance from the bottom of the button to the top is going to be 50 pixels as well. Okay. Now, what about Bezier curve identification? What about that variable? Well, it's going to have an object stored into it, and the object's going to be Bezier curve 1. So now Bezier curve identification is an object. You can now set attributes to this object, okay? And you've already stored what attributes you want changed on this object. That's what you've done. And there you go. So the first attribute you're going to have changed is the drawing object. Okay, you're going to have the drawing attribute. Okay, you're going to have the drawing attribute changed on this object, and it's going to be you're going to tell the computer to move the cursor to the 375th pixel. You're going to have it draw an arc, which is going to have two radii, one 50 pixels, the other 50 pixels. Okay, so, and then you're also going to have some other things. Only part of this arc is going to appear. Okay, you'll see three numbers. You see a 0 and a 0 and a 1. Now, if you have the number 1 as your third number, what's going to happen is the arc is going to appear on the top of the screen. Okay. However, if that 1 gets changed to a 0, the arc's going to go underneath, and you'll see that a little bit later. All right. So now let's go to this one. You're going to have some more variables. This is the second function. You're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. You're going to have 10 variables here. All right. All right, now I'm going to move down my notes just a little bit because I've already covered a lot of this. All right. Okay. So I'll get rid of all that. And now I've got that all covered. Now then, let me explain this to you one more time. If you were trying to draw a true Bezier curve, what would happen is you would have, instead of the letter A, you would have a letter Q. Okay. You'd have a letter Q like this, and then you would have a set of coordinates like, say, 375, 500. Okay? You'd have coordinates here. Arcs aren't run that way. Arcs are always radii. The Q and the C both, because the C represents cubic Bezier curve points, they will always have coordinates. Okay? And I'll explain that in my next presentation. All right. All right, now we're into the more interesting stuff. As I stated earlier, there is a second function on this JavaScript page. This second function is activated when the button on this web page is actually clicked. As you can see, this function starts by declaring variables, which I just stated. The next thing that happens is that an object is stored inside the SVG data variable. Okay, I realize that this object looks like a function, but this object now has properties and methods. Okay. This SVG data object, the first thing it's going to do is it's going to open an XQuery, and I'll show you that in a little bit. This XQuery will be used to retrieve the data from an XML document. This SVG data object will detect the opening and closing of this XQuery. The word get is a method of the SVG data object. Okay. The onReady state change is some kind of event connected to the SVG data object. In a future lesson, I will discuss these events in greater detail. The ready state event has different stages. And it's just like walking into a restaurant. When you first walk in the restaurant, you haven't placed your order yet. That value is 0. Okay, so you haven't requested anything, so therefore you are at 0. The next ready state sets up a request. Okay, so that would be like if you walked into a restaurant, you started reading the restaurant menu. Now you're setting up what request you're going to make. The next ready state makes a request. It's represented by the number 2. That's when you actually walk up to the counter and you order something. Okay. The next ready state processes a database request. That would be the equivalent. Now you're at number 3. Okay, you're at ready state process number 3. This would be the equivalent of the restaurant worker gathering your food and putting it on a tray to give to you. Okay. The final ready state in this thing is going to be the number 4. This is when you actually pay for the food and you take it with you. Okay. Now, either the clerk's going to put it on a tray, put your food on a tray for you, or it's going to be bagged up. It doesn't matter either way. The point is that in the end, you pay for it, you take it. That's number 4. Okay. So we now have a ready state, as you can see in the instructions. It's now at number 4. So what does the computer do once the ready state is at the number 4? Now, I want you to notice the double equal sign between the SVG data dot ready state and the number 4. You must use a double equal sign in this kind of a statement according to the rules of JavaScript. Okay, you have to show it's absolutely equal. Now, SVG data has a response text attribute, and the data you retrieve from the database has been successfully stored in this attribute. Unfortunately, you can't just use it from the attribute. Oh, no. You must store the value of the response text attribute into a variable, okay? Because otherwise you won't be able to use the data. Now this function is going to draw two Bezier curves. Our extra query retrieved the data for both curves. So that means that all this data needs to be separated. You got it from the database, now you need to separate it, okay? So first thing you're going to do is you're going to separate the data from the first Bezier curve and the data from the second one. So you're going to separate those two out. And that's what you're seeing right there in the code. Now, when you separate the first Bezier curve code from the second one, you also have to separate the data within the remember, you just stored all that Bezier curve information. You have to separate that information out further, okay? And that's what you're seeing in the code. Now, once all this data is separated out, you get to use your set attribute, which I just demonstrated to you earlier in the text, okay? Now, the SVG data.send event triggers the ready state change, okay? Now, this is very important. I want you to take a look very carefully at what I'm pointing to, because I'm pointing to those braces, okay? If you don't have the braces in the right order and the correct stuff, you're going to have some problems, okay? Now, the next thing is you will definitely want to use the document get element by ID for the text box to make sure that the data that you're getting from the database is what you're wanting to get out of the database, okay? You also want to make sure that the data that's in those variables is the data that you need in those variables. And you can use this document.getElementById by ID referencing the text box in order to do that. And you can go section by section by section to make sure that the data you're getting is what you need. Okay? Now, we're going to focus on the data that this web page is accessing. Okay? This data has been stored in something called XML. Nice thing about this thing is it's a text format, and it's really easy to send on the internet because it doesn't take up very much room. Okay. Now I formatted this data for a very specific purpose. Okay. And you say, well, why did you separate everything? What if you're trying to do an animation, and what you're really wanting to do is you're wanting to how shall I say this? You're doing an animation, and what you're wanting to do is you want to change one particular set of coordinates, but you don't want to change everything. Okay, you don't want to change the distance or whatever. You just want to change a set of coordinates. Instead of having to go through this entire statement where you have to read the thing from left to right to try to find which coordinate you want to change, you can just go through this XML document, find out exactly what you want to change, and then just change it real quick. You can see how the XML is very easy to read at this point. Okay. The problem is that all this data has to be validated. That's why you have to have this XML schema. Okay. Well, let's go ahead and take a look at the XML schema. Now, look at the bottom of this XML schema. Okay. This XML document has one main element to it. Okay. And then it has all these child elements after that. Okay. And so therefore, you want to reflect that in your schema. You want to say, okay, it's accessing this main element, and then it's going to access all these child elements, and make sure that they're all set in the way they're supposed to be. That's why you have a schema that validates your document. And that's why you got to run an X query on this and see if the document is valid. Okay. Okay. Because you have the SVG data element, and then the first child element of the SVG data is Bezier curve 1, and the second child element of SVG data element is Bezier curve 2. Okay. Now you notice that the Bezier curve 1 and the Bezier curve 2 elements have child elements of their own. So that's why we have a Bezier curve 1 type and a Bezier curve 2 type. You'll notice that the Bezier curve 1 type and the Bezier curve 2 type have identical child elements. This is perfectly acceptable. There are two other things you should notice. The namespaces in the XML document, the XML schema document, they match. And the XML document provides an address of the XML schema. So now we're constructing the XQuery document. Since the exist database upgraded since the last time I loaded an HTML lesson video, I wanted to take the time to point out a couple of changes that you have to make to successfully execute this XQuery. One thing you have to change is near the top of the screen. The other one's at the bottom, and I'll point these out with arrows. The first thing you will have to add is an import statement because it has to import a computer library into your project. Go figure. All right. So in order for this thing to process successfully, you have to import a library. But let's look at the end, at the bottom part of the XQuery. Okay, this is where you're going to find something called a JAX-P. What's a JAX-P? Well, this exist database program is running off of something called Java, not JavaScript, but Java itself. This is why I had to install Java 11. Okay, so the letter J in JAX-P stands for Java. Now, what about the letter A? Well, that stands for the acronym API, but there's a problem with this because API in itself is an acronym. What does that one stand for? Well, the first letter in the acronym stands for application. How many applications do you have on your smartphone? You call them apps, but they're really applications. Got a ton of them. Well, exist is an application. Go figure, huh? Now, you can't really store the exist database on your phone. It would take too much room. However, if you have a tablet, you can. So there you go. What's the letter P stand for? Well, it stands for the word programming. So what you're doing is you're using this application to program the exist database to execute your XQuery command. Okay. What is the letter I? Well, the letter I in API actually stands for interface. Okay, so you are interfacing with the exist database. When you're programming the exist database, you're interfacing with it. Okay, so you create XHTML documents or HTML5 documents. That's right, you're going to go up to HTML5 now. And you create JavaScript documents, cascading style sheet documents, XML documents, XML schema documents, and even XQuery documents. All right. The next letter, which is X in JAX-P, okay, JAX-P has an X in it. That stands for XML. You already know that acronym. The letter P stands for the word processing. So basically, you're using the Java computer language to process XML. And the exist database is the application you will use to execute Java code to process XML. Now, notice the letter XS. Well, this statement has a namespace, and that namespace can be found in the import module statement. The word Boolean is either true or false. That's what it is. Boolean represents true or false. So you can see there are two variables in this document. First one is instance, and the value of that variable is the location of the XML data. And then the other variable schema, which has the web address of the schema document. Okay, then we go ahead and validate this XML document. And you can see it's valid. Now, can you validate the XHTML, which actually is HTML5? Can you validate that? I'll show you how to do that in a future video. So I'm going to stop this for now because I have to add one more piece to this video, and I may be running out of time on this camera. So hang on, stay tuned. Okay, let's finish this lesson, shall we? Okay. All right. So what is this thing going to look like once we throw all this code in there? Well, take a look. You now have two arcs that are exactly the same size. One appears on the top, one appears on the bottom. And they are exactly the same size. You can see that for yourself. All right. Now, the information in this particular video can actually help you fix the double dollar project that we did way long ago. And it can also help you draw the soup can. Okay? Now you can form two arcs exactly the same size and draw the soup can. You can draw the wheels, not necessarily the wheels themselves, but that area, that wheelbase or whatever the heck you want to call it. You can leave the name of that down here in the description box below, but you can see, you can draw that too. And all kinds of neat little things. Sure you can. You now can make equally sized whatever. Now, as I promised at the end of this video, I was going to tell you why it took me so long to present this video. Now, why didn't I add my typical introduction to this video? It's just far too important. And I seriously doubt that anybody's going to watch this video unless they really are serious about programming. And I hope you are. Okay. So, the first reason it Bezier curves. You really don't explain this thing very well. What I needed to know is how to form perfectly equal-sized arcs, and they just didn't explain it at all. Not really. Okay? They didn't actually specify why the arcs are the way they are, especially with that radii. I thought those were coordinates, and that's what really threw me off. Okay? Now, not only did I read web pages, but I read books on the topic. And then on top of that, I actually had to watch several YouTube videos before I caught on. Hopefully you won't have to go through all that. That's what I'm sparing you from. Now, as I explained, the areas where the wheels of the car are, the soup can, all 9 yards, that's the reason why you have to know about equally sized arcs and how to draw them. Now, another hurdle I ran into was that things apparently have changed at the Exist headquarters, wherever that is. Used to, they just answered just about anything you had. That doesn't seem to be the case much anymore. I don't know if they are working as much on this stuff or what, but they're still friendly, but they're not as friendly as they were 6 or 7 years ago. Things have apparently changed, and that's really sad. But it got worse because I actually went to a place called Stack Overflow, and they're relatively nice people too, but they've been trying to push me into something that I don't want to be pushed into. And that is something called JSON. You say, well, what is JSON? Well, the letters JS stand for JavaScript, the O stands for object, and the N stands for node. Apparently, JSON is slowly taking the place of XML, and that's going to become quite a problem for me because I like running my databases off of XML. And I hope XML doesn't completely go away from me. But I will be learning JSON really soon, and I will present some JSON information. I don't like JSON as well. I mean, yes, it does work better with JavaScript, but it's not as readable as XML is. So XML, HTML, and now this JSON are open source computer codes. It's unfortunate that Microsoft is not, and they are becoming far more proprietary by the day, and I don't like that. So I'm going to try to stick with the Exist database as much as possible as I continue these projects. I suppose I could try to run this stuff from LibreOffice. It is free, but I don't understand it as well, and it could cause some complications there too. So some of the data that you would want to use probably can't. So, okay, as I noted earlier, the Q and the C are used for Bezier curves, Q for quadratic, C for cubic. They do actually have X and Y coordinates to them. Okay. I will also be covering in another video a topic called UTF-8. This list of special characters will be useful for you to use in future XHTML and now HTML5. You'll be able to use that UTF-8 in that. I will also discuss the topics of XML and XML schemas in greater detail in future videos. That concludes HTML lesson number 159. I hope you learned a ton. I will do my best to process this video as quickly as I can. I can't guarantee when this will pop up, but I'm sure you'll benefit from it. I will tell you more in a future video, so I'd like for you to stay tuned. Okay. I have been literally on this thing for about 2.5 hours now with a ton of brand new information for you guys. I will do my best to process this information and get it out to you as quickly as possible. I obviously will have to do another live stream to finish up all the notes. I thought I'd get further than I did. I'm sorry. I want to thank you guys very much for watching this presentation. I will tell you more in a future video, so I'd like for you to stay tuned.